this lecture we begin talking about second order LTI circuits. First we will start with zero input response, then we will study the zero state response, and then toward the end we're going to consider some general cases over various topologies. So let's therefore begin our subject for an input-free circuit, which we call zero state response. Okay. Now let's consider the following topology. It's called series RLC circuit. We have three components: an LTI resistor, an LTI inductor, and an LTI capacitor connected in series. They make a loop. Okay. R, L, C. Let's call this current IL. Note that there's only one current. So IL visits all the components, and let's call the voltage of capacitor by VC. Okay. Initial conditions are given to be IL 0 equals something, and VC 0 equals E0. Okay. Now let's obtain the differential equation describing the circuit through formulation variable capacitor voltage. So let our formulation variable be capacitor voltage, VC. Okay, so what we are aiming now is to obtain a differential equation, okay, in terms of VC and its derivatives. And we expect, well, we almost know that we're going to have a zero right-hand side because the circuit has no external input. Okay, so we consider the zero input response. So let's start from KVL, and then using the terminal equations and KCL, we will hopefully obtain the differential equation that we're looking for. So by KVL, the sum of these three voltages equals 0. So we have therefore VR plus VL plus VC equals 0. Okay, this is resistor voltage, inductor voltage, and capacitor voltage. Then VR is R times the capacitor current, IC, plus VL is L dIL by terminal equation of inductor. Okay. So L dIL, and IL is same as IC. Okay, so L diC, okay, plus VC equals 0. And now by using the terminal equation of capacitor, we can replace those ICs by an expression in terms of VC. Okay. That yields the following: R C dVC. Okay, so that's what IC is, plus L diC. Okay. So IC is CdVC, therefore we have another derivative operator here. That means LC d squared VC, and finally we have VC. Okay. So that equals 0. So what we use here is the terminal equation for capacitor. IC equals C dVC. Okay. Therefore we have obtained what we were looking for, an expression only in terms of the capacitor voltage. So let's rewrite that equation so that the highest order term has the coefficient 1. So that means we have to divide both sides with LC. Then we have d squared VC plus R over L dVC plus 1 over LC VC equals 0. Okay. Right hand side is 0 because we have no input in the circuit. So this is our differential equation. Okay. Now this is second order differential equation because highest order term is double differentiation. To obtain a solution, we need therefore two initial conditions. Initial condition of the capacitor voltage and initial condition for the rate of change of capacitor voltage. Okay? So what are the initial conditions? VC0 and dVC evaluated at 0. Okay. Now VC0 is directly given V0, so dVC0 we have to obtain somehow from the given initial condition information. So VC0 equals V0, this is given, and dVC0 equals, again, we can use the terminal equation. So dVC0 equals IC0 over C. And by KCL, IC and IL, they are the same current, therefore that equals IL0 over C, that is I0 over C. So that's the initial condition for the DC dot. Okay. So, using the differential equation constraint plus the initial condition constraints, we can obtain the unique solution for this circuit in terms of the capacitor voltage. Now, what would have happened had we chosen a different formulation where, for instance, the inductor current? Okay, what would the differential equation look like in that case? So let's try and see it. Formulation variable is now formulation variable now picked as IL. Okay, remember that we're dealing with this circuit. Let me redraw it here. Okay. Plus minus VCC, this is IL, this is L, this is R. Okay, again, let's start from KVL, okay, VR plus VL plus VC equals 0. This time we want to express everything in terms of IL and its derivatives. Okay. So let's do that. VR is R, IL, clearly, okay, plus minus VR is L, R, IL. Then we have VL, which is by terminal equation of the inductor, it's L DIL. And we have VC. What's VC? VC is VC0 plus 1 over C. 0 to T, IC, tau, d tau, and IC and IL, they're the same. So we can put inside the integral IL, and that equals. Note that this is constant, and we don't want any integrals in our differential equation, because it won't be a differential equation in that case. So let's get rid of that, this constant and that integral, and we can easily do that by differentiating both sides. Okay. So that implies R dIL plus L d squared IL, and then we differentiate, get this constant disappears, and we have plus IL over C. Okay. And that equals 0. From this line to that line, all we did was we differentiated both sides. The derivative of 0 is 0, so the right-hand side didn't change. So that's our differential equation. That is an equation only in terms of our formulation variable. So let's rewrite it so that the highest order term appears with unity coefficient. So then we have v squared IL plus R over L DIL plus 1 over LC IL equals 0. Differential equation. Note that the coefficients of the respective terms are the same in both differential equations, despite the fact that the formulation formulation variables are different. So that's no coincidence, okay? So regardless of the formulation variable, you will always obtain the same differential equation. Okay, so let's figure out the initial conditions. So in this case, since the differential equation is in terms of IL, we require IL0 and DIL0. So we have IL0 equals I0 automatically because that's given. And we have to figure out the IL0 from the given information, namely IL0 and VC0. So let's do that. DIL0 equals 1 over LVL0. What we did, we used the terminal equation for the inductor. And what's VL0? Okay. So 1 over L times. Now VL is minus VR minus VC. Okay? And VR is R times IL. So what we have is minus RIL0. So this is minus VR0 minus VC0. Okay? Therefore, we have minus R over L 0 minus 1 over L V0 for the initial rate of change of inductor voltage. Okay. Now, we will talk about the solutions or the formal solutions for such second order homogeneous differential equation. Now, the right-hand side, or excuse me, the left-hand side of the differential equation gives us an object which we're going to call the characteristic polynomial of the differential equation, or characteristic polynomial of the circle. Okay. And characteristic polynomial usually denoted by dfs, such that you look at the differential equation and you look at its coefficients. It's a second order differential equation. So from this you construct the following polynomial equals s squared. Okay, so d becomes s, and the coefficient of the highest order term is 1. Therefore, we have 1 times s squared plus r over l s, so that describes the first order term, and we have the zeroth order term, okay, plus 1 over else. Okay. So the coefficients gave us the characteristic polynomial. And it's a very important object, characteristic polynomial, because it tells us a lot about the form of the solutions. In particular, the roots of the characteristic polynomial tell us about the form of the solution. So in general, and sometimes, okay, let me put it here, characteristic equation is another term that people use, and by characteristic equation we mean characteristic polynomial set to 0. That is the equation, the solution of which are the roots of characteristic polynomial. Now, in general, characteristic equation can be written as s squared plus 2 alpha s plus omega 0 squared equals 0. Okay? For our case, 2 alpha is r over l, and omega 0 squared is 1 over s. Then the roots of this second order equation are S1 and S2. We have at minus alpha plus minus square root alpha squared minus omega 0 squared in terms of the coefficients of the polynomial. Now we introduce important definitions that we will be using a lot. Roots of characteristic polynomial are what we will be calling natural frequencies. Okay. Of the differential equation, and since no matter what formulation variable you choose, you will always obtain the same differential equation about the same coefficients. Those are also called natural frequencies of the circuit. Okay. Sometimes other words are also used. You may have heard eigenvalue or mode. They all mean the same thing. Okay. And omega 0, which is square root of 1 over square root of LC, is called the resonant frequency. It's called the resonant frequency. Okay, so now we will talk about, depending on the root locations or the natural frequency locations on the complex plane, what type of response we get from the circuit. Okay. So solution of the circuit depends on the locations of the roots of the characteristic polynomial, or locations of the natural frequencies of the circuit on the complex plane. Okay. And we will be dealing with 4 cases. 4 cases are possible, at least for circuits that contain only passive components, for passive circuits. So we have this possibility. This is the imaginary axis, this is the real axis, the origin, and we have a natural frequency here, and we have another natural frequency here. So S1 and S2, both negative and real, also they're different from one another. This case is called overdamped. So that's one possibility. Another possibility is that those 2 roots coincide with one another. S1 equals S2, and both negative. So this case is called critically damped. Then, more interesting cases occur when we have complex roots. Okay, so this is case 3. When we have complex natural frequencies, and since we will always be dealing with real polynomials with real coefficients, or differential equations with real coefficients, the complex roots must appear as conjugates of one another. So S1 equals S2 complex conjugate. So they have the same real part, but imaginary parts, they differ in sign, but same magnitude, with real part negative. This is called the underdamped case. Okay. And in the extreme, we have the following case where it's a special case of, in a sense, underdamped, but it has a different name, where the real part is 0. Okay, so the roots are purely imaginary. S12 equals plus minus j omega 0. So this case is called the lossless case. 0, real, imaginary. Now, through some simple examples, we will go through each of these cases. Let's start from the first case, case 1. Case 1. So that happens when alpha, okay, is larger than omega 0. And we're always dealing with positive or non-negative coefficients. Okay. This is when the circuit is overdamped. Okay. So remember alpha and omega 0, they appear in our characteristic polynomial as s squared plus 2 alpha s plus omega 0 squared. So those are the coefficients in our characteristic polynomial. Okay. So S12, the roots are at minus alpha plus minus alpha squared minus omega squared. And suppose that the outcome of that square root is what we call alpha d. Okay? Therefore, we have minus alpha plus minus alpha d. Both alpha and alpha d, they are positive, and the magnitude of alpha d is smaller than the magnitude of alpha. So we have here both roots are real and they're negative. Okay. So the natural frequencies are real, okay, negative, and distinct. Okay, so that means they're different from one another. So in this case, the solution, suppose that we're dealing with capacitor voltage, the solution has the following form: K1 e to the S1t plus K2 e to the S2t. Okay, so this is the homogeneous solution, which is the entire solution, because we're considering the zero input case. Okay. Not that, unlike the first order case, now we have two unknowns in our homogeneous solution, and those two unknowns we figure out using the two initial conditions, namely the initial condition for VC and also initial condition for dVC, the rate of change of capacitor voltage. Okay, so let's consider a very simple example for the overdamped case. Example: R equals 3/2 ohms, L equals 0.5 Henry and the capacitance equals 1 farad. Remember that we're dealing with, for now, the series topology. Okay, so we have 1.5 ohms, 0.5 Henrys for this guy, and 1 farad for the capacitor. Okay, now that, together with the initial conditions, 2 volt and IL0 equals 10 amps, is what we will be dealing now. So the differential equation yields d squared Vc plus R over L dVc plus 1 over Lc Vc equals 0. Okay, so that's the differential equation describing the evolution of the capacitor voltage. And how about the initial conditions? Vc0 equals 2 volts and dVc0 equals IL0 over capacitance C, which is 10 volts per second. Okay, that unit is volts per second because the variable is rate of change of capacitor voltage with respect to time. So the characteristic polynomial E of S in this case is, you look at the left hand side and you look at coefficients. What you have is S squared plus 3S plus 2. And the roots of that characteristic polynomial are what we call the natural frequencies of the circuit, and natural frequencies of the circuit appear in the solution as these exponents. Now clearly this can be written as S plus 1 times S plus 2, and when you write it in that form, it's clear that natural frequencies are at -1 and -2. Okay? So both real negative and they're distinct. Natural frequencies S1, 2 are at -1 and -2. Therefore, capacitor voltage should look like K1 e to the minus t plus K2 e to the minus 2t. And K1 and K2, they are to be determined by the initial conditions. So let's do that. Vc0, we give it to be 2 volts. So plug in t equals 0, so what you have is K1 plus K2, and that equals 2 volts. And for the Vc0, you differentiate it and then plug in t equals 0. In that case, you have minus K1 minus 2 K2 equals 10. Okay. So 2 equations, 2 unknowns, the solutions turn out to be K1 equals 14 and K2 equals minus 12. Okay. Therefore, capacitor voltage for future times is 14 e to the minus t minus 12 e to the minus 2t volts. Okay. 14 positive. Okay. Now let's move on to the other case. Case 2, alpha equals omega 0. Remember that. The characteristic polynomial was, according to our notation, s squared plus 2 alpha s plus omega 0 squared. If that alpha and that omega 0 are equal to one another, we're dealing with the critically damped case. Okay. For the series RLC circuit, that means in terms of the circuit parameters, R over 2L, so that's alpha equals 1 over square root of L, and that's omega 0. Now, the characteristic polynomial ds equals s squared plus 2 alpha s plus omega 0 squared. Now, if alpha equals omega 0, then this can be written as s plus alpha squared. And it's clear that both roots of the polynomial are at the position minus alpha. Natural frequencies are at minus alpha and minus alpha. So both are at minus alpha. In that case, the solution, the general solution, has to have the following form: k1 e to the minus t plus k2 t e to the minus t. In other words, e to the minus t, and then that's multiplied by not a constant but a first order polynomial, k1 plus k2 t. Okay, so this is the form of the solution for the critically damped case. Now let's, over a simple example, study the critically damped circuit. Example. R equals 1 ohm, L equals 1 Henry, and C equals 4 farads. Okay? So we're constantly series RLC topology. And the initial capacitor voltage is 2 volts and initial inductive current is given to be 4 amps. Okay, let's, for this situation, figure out the solution, VCT. So the differential equation is dVC plus 1 over 4 VC equals 0. And VC0 equals 2 volts given, and dVC0, which is the initial condition for the differential equation, is IL0 over C, which is 1 volt per second. Okay. And for this, let's figure out the solution. The characteristic polynomial equals, we look at the differential equation, and it tells us what the characteristic polynomial is: s squared plus s plus 1 over 4. This can be written as s plus 1/2 squared, which tells us immediately that both roots are at minus 1/2. So the natural frequencies of the circuit are at minus 1/2 and minus 1/2. Then we can write the solution as k1 times e to the minus t over 2 plus k2t times e to the minus t over 2. And we figure out k1 and k2 using the initial conditions for the differential equation. Okay, so VCT equals, or the form of VCT is k1 e to the minus t over 2 plus k2 t e to the minus t over 2. Because we're dealing with the critically damped case. Okay, so we see 0 equals, when you plug in t equals 0, due to that t term, that second term disappears, and what we have is k1. And VC0 is given to be 2 volts, therefore k1 is 2. And dVC0 equals minus 1/2 k1, and from the guy we have plus k2, and that equals 1. Okay. And then we have k1 equals 2 and k2 equals 2. Okay, so both coefficients are at 2. Hence, capacitor voltage VCT can be written as e to the minus t/2 plus 2t to the minus t/2 volts. Okay. For all future times. Okay, now let's move on to the third case. Okay, underdamped. Case 3. Omega 0 larger than alpha. Underdamped. Characteristic polynomial is 2 alpha s plus omega 0 squared. If omega 0 is larger than alpha, then this means that we're dealing with complex roots. Natural frequencies S12 equals minus alpha plus minus j omega d. So this is the frequency of damped oscillations, where omega d is defined as omega 0 squared minus alpha square, the square root. Okay, so when that is the case, capacitor voltage and also the other variables in the circuit start to display oscillations, and because this we have a non-zero real part for the root, those oscillations will not last forever, but they will be decaying, okay, as time goes on. And the general solution has the following for k1 e to the minus alpha t sine omega dt plus k2 e to the minus alpha t cosine omega dt. Now let's see a numerical example that displays decaying oscillations as there. For the series RLC topology with resistance value 3/25 ohms, inductance 1 millihenry, and capacitance 0.1 farads. RLC. Initial capacitor voltage is 3 volts and initial inductive current is given to be 14 amps. Okay, for this case, let's obtain the capacitor voltage. Okay, so the differential equation is d squared BC plus R over L dBc, which makes 120 in this case, plus 1 over LC BC, which is 10,000 equals 0. So that's our differential equation. And we need initial conditions for this differential equation. VC0 is given, and dVC0 is initial inductor current over the capacitance, which is, in this case, 140 volts per second. Okay. Now let's obtain the solution for VCT. For that we require the roots of the natural frequencies, and for natural frequencies we need the polynomial, characteristic polynomial, okay, which the natural frequencies belong to as the roots. So ds, the characteristic polynomial, is directly coming from the differential equation, s squared plus 120s plus 10 to the 4. And that can be written as s plus 60 squared plus 80 squared. Okay. And if you solve the equation d of s equals 0 to get the natural frequencies, to get the roots, what you have is you have complex solution. Okay. The roots are at minus 60 plus minus j 80. Natural frequencies, or the roots of the characteristic polynomial, or the eigenvalues of the circle, or the nodes, modes of the circle, sometimes called the poles of the circle. They have a lot of names. Okay, are at minus 60 plus minus j 80. Okay, so that tells us the form of the capacitor voltage. Okay. So we can write that the capacitor voltage should be of the form K1 e to the minus 60t. Okay. So that exponent is coming from the real part of the natural frequency, sine 80t. And this frequency is coming from the imaginary part of the natural frequency. And we have another term with cosine plus k2 e to the minus 60t cosine 80t. Okay, now let's determine k1 and k2, and for that we use the initial conditions. Vc0 equals, okay, plug in t equals 0, the sine term disappears, and what you have is k2. Okay, and that must equal 3. Then differentiate this, and then plug in t equals 0. Vc0, then you have 80 k1 minus 60 k2, and that must equal 140. Okay, that yields k1 equals 4. So k1 and k2 are now determined. That means we have our solution. Hence, capacitor voltage must be 4 e to the minus 60t sine 80t plus 3 e to the minus 60t cosine 80t ohms for all future times. Okay, now let's spend a little bit more time on this solution, on the oscillations, so we have a better understanding of what's going on as time goes on. For that, it may be helpful to rewrite this in a slightly different form. Okay, so note that we can write the following. VCT equals e to the minus 60t because it's common to both terms. And then we have 4 times sine 80t plus 3 times cosine 80t. Now our aim is to write this as a single sinusoidal function. Okay. So for that, what we do is we consider this 4 and 3 as the coefficients of a vector in R2. And then the magnitude of that vector, or the length of that vector, is this guy squared plus that guy squared, and then you take the square root. In this case, it's 5. Okay, so that equals 3 squared plus 4 squared square root. So what we do is we multiply and divide by this magnitude. Okay. So what we have here is 4 over the magnitude 4 squared sine 80t plus 3 over magnitude cosine 80t. Now why we did this is that if you write it as such, now sine, here we have a coefficient and here we have another coefficient, and those coefficients are such that this guy squared plus that guy squared equals 1. So that means if you consider these as the coordinates on the two-dimensional, on the plane, that means that coordinate corresponds to a point on the unit circle. Okay, so that means these two numbers we can express as the cosine and sine of some angle. Okay. So let's call this cosine phi, and let's call this sine phi. And what's the angle phi? It's arctangent 3 over 4. Okay, phi is arctangent 3 over 4. Okay. Hence, by using the trigonometric identity, sine alpha cosine beta plus sine cosine alpha sine beta equals sine alpha plus beta. Okay, using this trigonometric identity, we can rewrite this sum of terms as a single sinusoidal function. Okay, VCT therefore equals, this is 5, then we have e to the minus 60t, and this sum can be written as a single sine. Sine 80t plus arctangent 0.75. Now this is easier to interpret or easier to visualize. What we have is, first we have a sine term, okay? And what we know about that is, besides that it's always between plus and minus 1. Okay, its magnitude is never larger than 1 because it's a sine function. And then that's multiplied by this term, which decays as time goes on. So therefore we can visualize it as follows. VCT. Okay. Now let's forget about that sine and sketch 5 times e to the minus 60t. It has this monotonic shape that decays to 0. Also, so this is 5. Let's throw minus 5 times e to the minus 60t. That is the mirror reflection of this guy with respect to the horizontal axis. In that case, we have something like this. Okay, and this is minus 5. So what we have drawn is 5 e to the minus 60 here, and this is minus 5 e to the minus 60. And those two curves together are called the envelope. of VCT. Now what happens to VCT is, it can never, since sine is always of magnitude 1 or less, it can never leave the envelope. Okay, so it starts at 3, okay, and then it oscillates with frequency 80 radians per second, and slightly, or it's converging to 0 by making oscillations. So the shape will look like something like this. Every once in a while it will touch the envelopes. And so on. Okay. In our last case, we will consider the situation where the electrical energy in the circuit is trapped. It's not leaking out of the circuit. Energy is conserved, and that would correspond to in series RLC circuit without our sustaining oscillations. Case 4. Omega 0, resonant frequency is positive and alpha is 0. So this case is called lossless. And for the series RLC topology, it means R equals 0. Okay, 0 resistance or infinite conductance. So what we have is L and C come in series, or they're in parallel, depending on how you look at it. So the differential equation is now without a first order term. It has this form: d squared Vc plus 1 over Lc Vc equals 0. Because the first order term was, the coefficient of the first order term was R over L, and now R equals 0. Characteristic polynomial d of s reads s squared plus 1 over Lc, or s squared plus omega 0 squared. Natural frequencies S1, 2 are x plus minus j omega 0 plus minus j 1 over square root of Lc. Okay, this is sometimes called Lc oscillator. And the solution has this form: K1 sine omega 0 t plus K2 cosine omega 0 t, and which, like the trick that we used in previous example, can be written as a single sine or single cosine with some non-zero phase. So this corresponds to sustaining oscillations. That is, the oscillations will always keep going with the same magnitude, whereas the oscillations here, the magnitude becomes smaller and smaller as time goes on. So they're decaying to 0, but whereas here in this case, the oscillations keep forever at the frequency omega 0 with constant magnitude or amplitude. Okay? Because the energy is now nowhere to leak out of the circuit. We're considering the ideal case where we have no resistance. Okay, let's apply this to a numerical example. R equals 0, L equals 1/2 Henry, and C equals 1/2 farads. conditions are given as VC 0, 10 volts, and IL 0 equals 10 amps. Differential equation, d squared VC plus 1 over LC VC, which is 4 in this case, 4 VC equals 0. VC 0 is 10 volts and dVC 0 is 10 over 1/2, 20 with units, volt per second. Now, the characteristic polynomial reads s squared plus 4. So this is s squared plus 4, and this yields the natural frequencies S12 equals plus minus J2. Okay. Therefore, VCT equals K1 sine 2t plus K2 cosine 2t. To figure out K1 and K2, we use initial condition constraints. Plug in t equals 0. Okay. We have K2 because sine disappears at t equals 0, and K2 must equal 10. And differentiate and then plug in t equals 0. This time you have 2K1 equals 20, yielding K1 equals 10. Therefore, we have VCT equals 10 sine 2t plus 10 cosine 2t. And that can be written as a single sinusoidal function by using the approach that we did in the previous example. If you do that, we have 10 square root of 2 sine 2t plus, I have 4 radians of 45 degrees. Okay, so that's a solution for t greater than equal to 0. Note that these oscillations at 2 radians per second go on forever. There is nothing to attenuate it. Okay, there is no exponential function attenuating it. And what it looks like is, okay, the amplitude is about 14. T seconds. This is VCT volts. 10 square root of 2 minus 10 square root of 2. This is 0. So initially you're at 10. Okay. So you're somewhere here. And then what happens is the oscillations go on forever at 2 radians per second. That's the lossless case. Now, before we end this lecture, let's very briefly talk about why this case is called lossless. Why we're calling this lossless. Okay, so this is the situation. We have an inductor and a capacitor connected in series or parallel, depending on how you look at it. Let's call this voltage V. Let's call this current I. This is L. This is C. V is capacitor voltage and I is the inductor current. Now, total stored energy in the circuit is the energy stored in the capacitor plus the energy stored in the inductor. Okay. So V of t therefore equals 1/2 L IT squared plus 1/2 C capacitor voltage squared. So this is the energy stored in inductor at any given time, and this is the energy stored in the capacitor at any given time. Okay. Now let's, without using the solution of I of t or V of t, let's directly differentiate the energy, okay, E of t. dE over dt equals what? So here we have I LdI, okay, Li dI plus CV dV. Okay, so that's the derivative of this term, and this is the derivative of the stored energy in the capacitor. That we can write as I times L dI plus V times C dV. Okay. Now what's LDI? LDI is the inductor voltage. Inductor voltage is V. So this is V. And how about CdV? CdV is the capacitor current. Capacitor voltage is polarity is plus minus like that. Therefore, this is the direction of the capacitor current. And this is the direction of the inductor current. Therefore, by KCL, it's minus I, minus inductor current. Okay. So what we have, therefore, is IV minus VI. And that's always 0. Now, since rate of change of energy is 0, it means whatever the initial energy is, the energy remains constant at that value. Okay. So we have ET equals E0. Once again, that's because E dot equals 0. That means E is a constant function, constant sigma. For all T greater than or equal to 0. Therefore, the energy, electrical energy, that's trapped in the circuit at the initial time can never leave the circuit in the future. And we say electrical energy is conserved. Okay. Well, we always use that the term energy is conserved, okay, for all situations, but in that what we mean is it changes form. Whenever we have a resistor in the circuit, electrical energy is transformed into the heat energy and escapes from the circuit. Okay? But in this case, there is no transformation. Electrical energy remains, the energy remains in electrical flow for all future times, and therefore we can use the statement electrical energy is conserved.